Hello everyone, thank you for listening to my talk. My name is Boyang Liu and I'm a postdoc research assistant working for University of Oxford in Material Science Department. Today I want to talk with you about my research in solid-state batteries and how I use focused ion beam SEM to help me in my research. At the beginning, I want to talk with you about the basic principles of the solid-state batteries to give an idea of why I research about these kind of things. To compare with the conventional battery, the difference in our solid-state battery is that it uses a ceramic material to replace the liquid electrolyte inside the conventional batteries. And this change will bring in some advantages. First, the safety and non-flammability, and also lower hazard, and also the possibility for higher energy electrode, especially for lithium metal anode. However, despite these kind of advantages, there are a few challenges of the solid-state batteries before it can be put into practical applications. Besides of the material property itself, there are some key challenges of the batteries at the interface against the electrode. As we can see in this schematic here, for different interface against cathode and lithium metal, there are different challenges. For the cathode interface, the challenge includes the interparticle contact issue and also the chemical-mechanical degradation issues. And for the lithium metal anode interface, the challenge is mainly about dendrite growth, which can cause internal short circuit. The reason of this kind of contact issue and chemical instability is because of the nature of the ceramic itself. Now I'm going to talk about how I use our equipment to help us in my solid-state battery materials research. So this is a photo of our plasma FIB inside our department. And I always use it for my battery test. So this schematic shows how the FIB SEM works. There are two beams inside the chamber, one to generate electrons to test the SEM image, and the other is to generate ions to eliminate materials and create cross-sections. When we operate a FIB SEM, first we turn on the ion beam to cut off some part of the material to generate a hole inside the surface, and then we cut off one side of the hole to make it flat and nice. And after that, we use the electron beam, which has an angle from the ion beam, to see the morphology from the surface. As a special technique inside the SEM, plasma FIB has a certain dimensions which is best for use. It is kind of in between of X-ray CT and TEM. The best dimensions for it is between 0.1 microns to about 100 microns. Now I'm going to talk about the application of FIB SEM in my battery research. As I just mentioned, a solid battery is composed of different sections, including metal anode, solid electrolyte, and composite cathode. The composite cathode is composited of active materials and solid electrolyte particles. So these three sections has two interfaces in between of them. My interesting point is how to test the interface properties by the FIB SEM. We use FIB SEM to see first the lithium metal to solid electrolyte interface to see the contact and the dendrite issue. Second, the electrolyte itself, the electrolyte structure, including its densification, the pores, and the composition of the electrolyte. Third is the cathode to electrolyte interface, including the particle contact and chemical reactions. In this slide, I put an example of a plasma FIB image that I got, which is cross-section of a composite cathode. It is composed of cathode active materials and a solid electrolyte. This low magnification image is to give you an idea of how we operate the FIB SEM. The big hole is cut by the ion beam, and we also use the ion beam with a smaller signal strength to create the flat surface here. And after we generate a flat surface, we use the electron beam to test the morphology, and also we test the chemistry of the surface by EDX signals. So these two higher resolution images shows the ITM and EDX images on the surface. From the ITM, we can tell the morphologies of different particles. We use different grayscale of the particles to identify the different materials because they have different electron densities. And from EDX image, we can also clearly see the different particles by their chemistry distributions. Now, I want to give you an example of how I use this kind of technique for my battery research. A project that we have done is try to understand the microstructure change of the composite solid electrolyte over battery cycling. That is to understand the composite cathode part inside the solid battery. The cathode had the issue is that the volume of the cathode particles can be changed over battery cycling. And this volume expansion and shrinkage will cause contact loss and also reduce capacity as a result inside the battery. So here we use pre- and post-cycling FIB-SEM to see the mechanical degradation inside the composite cathode with different conditions. The results are shown here. First, we cycle the cell at a quite low stack pressure, and we can see the capacity drops fast from the first to the 50th cycle, and the capacity is represented by the blue dot curves. To understand the reason why it drops fast, we did FIB-SEM and 3D reconstruction to see the morphology inside the composite cathode before and after cycling. These are the two images. One is before cycles and one is after cycling. This is both tested for the composite cathode. It is composed of different materials, so we represent them with different colors. The green section is the cathode active material. The purple and yellow are for the solid electrolyte, and the black part is for the empty space. We can see here before cycles there are not much black space because we use a quite high pressure to form the cell. But after we do 50 cycles, we can see there are much empty space generated in between of the active material and solid electrolyte, which is a result of the cathode volume change, and it generates capacity decay. And with a higher stack pressure or with a lower voltage window of the cell, we can get a much more stable capacities inside the cell. And after cycling, we also test the FIB-SEM 3D reconstruction to see the morphology change. Here we can see, if we compare with the left side, we can see with the stable capacity, the morphology is much more stable and there is not much empty space generated. So this work used the SEM to test the morphology change over a battery cycles and correlate it with the capacity stability. As a conclusion, I think FIB-SEM is powerful for battery research, and it can be applied to observe the microstructure, component chemistry inside the cell. And FIB-SEM can help understand the mechanical and chemical degradations during the process and for failure analysis. Thank you.